Yeah, so I'm Laura, and today I'll be talking about an implementation of proofs of quantumness on an ion-trapped quantum computer, which is a merging of these two works here. Okay, so as you all probably know, recently there have been a lot of displays of quantum advantage or quantum supremacy. Probably the most well-known is the Google groups in 2019, but there have also been other results from, for example, USTC in China in 2021, and et cetera. But one of the issues that we see with these quantum advantage results is that the demonstrations are very hard to classically verify. And specifically when you take, for example, the Google result, they're trying to do this problem called like random circuit sampling. And when they do this, they need to validate the results using the linear cross-entropy benchmark, which takes exponential time to compute classically. So this then leads to the question, how can we come up with tests of quantum advantage that are classically verifiable? And that's really the focus of this work. So in particular, in this work, we implement protocols called cryptographic proofs of quantumness. I'll go over what those are exactly in just a few slides. And we implement them on 11 qubits on an ion-trapped quantum computer. So obviously, because this is on 11 qubits, it's not exactly quantum advantage, but we expect that when you suitably scale this up, this can lead to classically verifiable, efficiently classically verifiable quantum advantage. And we implement these protocols in two different ways, interactively and non-interactively, and again, I'll go over what exactly that means in a bit. Okay, to provide an outline for the talk, so first I'll go over background in quantum cryptography, so what exactly are these cryptographic proofs of quantumness, and then I'll go over also the primitives that we build these protocols off of, and that's specifically these trapdoor claw-free functions. And I'll go over the interactive protocol, specifically what we do, along with the results, as well as the non-interactive protocol and the corresponding experimental results. Okay, so first let's go over some quantum cryptography. So an interactive cryptographic proof of quantumness is an interactive and efficient test that a quantum computer can pass, but a classical computer can't. And this is based on some cryptographic assumptions. So if you break the underlying cryptography, then this doesn't work anymore. Okay, and in particular, what do I expect from these protocols? So suppose you have a classical verifier, and you have a quantum prover, and the verifier wants to delegate some computation to the quantum prover and be able to verify that the answer is correct. So in particular, the verifier can send over to the prover some setup, so this can correspond to parameters or something defining the problem that the verifier wants the prover to solve. And the prover then has to give an answer back, and this initial answer is called the commitment. And what's special about the commitment is that in later rounds of interaction, the verifier sends over a challenge or just some sort of question. And the prover needs to send over back a response. And so the thing about the commitment is that the commitment has to be consistent with all these later responses of the prover. So they're already committing to an answer that they have to remain consistent to. And the reason why this is called an interactive protocol is because there are these multiple rounds of communication between the verifier and the prover. And we also require that this is verifiable, and what that means specifically is if the quantum computer does perform this task, then the prover performs the task and the verifier will accept. And on the other hand, if the prover turns out to be, say, a classical computer in disguise, or doesn't do the protocol as stated, then the verifier will reject. Okay, and this is an interactive cryptographic proof of quantumness. So in order to construct such protocols, we need a certain cryptographic primitive, which is known as a trapdoor claw-free function. And so in particular, this is just a function, but it has some special properties that I'll go over. So the first property is that this function is 2 to 1. So for any output y, output of the function f, then it requires two different preimages, x0 and x1, which both map to the same y. And another property that we require is that this is claw-free. And claw-free means that given some output, it should be hard to find these two inputs, x0 and x1. And moreover, we require a trapdoor. And a trapdoor just means that for any output, if you're also given some sort of secret information, which is known as the trapdoor, then you can efficiently find those two preimages, x0 and x1. So basically, you can think of this as just a 2-to-1 function where it's hard to invert unless you're given this trapdoor, and then it suddenly becomes easy to invert. Okay, and we obtain these different properties of trapdoor and claw-free and 2-to-1 by basing them off of certain cryptographic assumptions. And so in particular, in this work, we construct TCFs based on the factoring problem and learning with errors. Okay, so now I'll go over specifically the protocol that we implement. And so remember, we again have the classical verifier and the quantum prover. And first what happens is the verifier will generate their TCF together with a trapdoor. And so this usually consists of sampling the correct parameters. So in particular, with learning with errors, then this would be sampling some matrix and a secret vector. And so the verifier then first sends over that trapdoor claw-free function to the prover. But notice that they do not send the trapdoor. The trapdoor is their verifier's own secret piece of information. And the prover then, as their commitment, they send over some image of the function. And the verifier then has two different challenges that they choose at random. And the first challenge is the preimage test. So they're asking for a preimage. And it's exactly what it sounds like. The prover sends over some x such that f of x is equal to y. And here we can see that this is efficiently verifiable because we just have to check that f of x is equal to y. And f should be efficiently computable. So this was the first step. This is called the preimage test. And the second challenge is something called the equation test. And so if the verifier asks for an equation, then the prover then needs to give a bit string d such that this equation is satisfied. So in particular, we require that d dotted with x0, xor, x1 is equal to 0, where this dot and the xor are just multiplication and addition respectively, modulo 2. And these x0 and x1 correspond to the preimages of the output y that the prover previously committed to. And again, we can see that this is efficiently verifiable because the verifier is given the output y, and using their secret trapdoor, they can efficiently invert the function f, so they can find these x0 and x1, and then verifying that this equation is true is fairly clear. So I would like to claim in this interactive protocol that if the prover is indeed quantum, then they would be able to do both of these tests with 100% probability. So let's show exactly what the strategies are. So we can consider this quantum circuit. And this first register of qubits corresponds to the qubits that store the inputs, so the x's. And the bottom register should store the output of evaluating the function. And so first, all that happens in this quantum strategy is that the prover needs to evaluate the function f on a superposition of all possible inputs x. So this UF is just a unitary corresponding to evaluating the trapdoor claw-free function. And then what they need to do is they need to measure. So they measure the output register, and they get this Y. So that's how they get their commitment, their output image. And what happens is that one can show that the preimage register, the register corresponding to storing inputs, then collapses to this equal superposition over the two preimages, x0 and x1, that correspond to that output Y that they measured. And so clearly, just by measuring this top register of qubits, then they can obtain the preimage. So they can obtain one of the two preimages with equal probability. And this is how they pass the preimage test. On the other hand, for the quantum strategy, for the equation test, the only difference here is this extra layer of Hadamards. Okay, so recall before there were no Hadamards up here, and the differences in the equation test we're adding those. And the reason why this then works to satisfy the equation is by an argument pretty similar to Simon's algorithm. And so you can show that upon performing this circuit and measuring to obtain a bit string d, then the bit string d should satisfy this equation. Okay, and this is essentially the protocol. And so what happens is when the prover first is asked to commit to their bit string, they should measure only the bottom register and then wait for when the verifier asks for either pre-image or equation test. They then decide whether or not to apply these Hadamards, and then they'll measure the top register as well. Okay, so this was showing how a quantum computer can perform this task perfectly. But what about a classical computer? So if we require the TCF to satisfy an additional property, then the protocol gives a quantum classical gap. So in particular, this property is called the adaptive hardcore bit. And what this essentially means is that if you have one of the inputs x0, it should be hard to even know a single bit of the other preimage. And so with this additional property, you can show that classically we must satisfy this inequality. And so P pre here is the probability of passing the preimage test, and PEQ is the probability of passing the equation test. So we require that P pre plus 2 PEQ is less than or equal to 2, and that's the best that a classical computer could ever do. But meanwhile, in the previous two slides, we showed that quantumly, P pre and PEQ can both be equal to 1. And so in particular, we can get that this whole equation is equal to 3. So in order to have this quantum advantage over classical, then we just need to have P pre plus 2 PEQ greater than 2. And so this was assuming that we have this additional property known as the adaptive hardcore bit. But if we don't have it, you can also do this as well, and you can show a similar quantum classical gap. But the protocol has to be modified slightly in that it requires an additional round of interaction. But the gap, yeah, it's pretty similar. And in particular, the factoring protocol, the protocol based off of the problem factoring in this work, didn't have the adaptive hardcore bit, and we did perform this protocol. But for the sake of time, I don't have time to go over exactly this protocol, so I'll just focus on the theory of the learning with errors one. Okay, so now let's talk about the experimental results. So here on the left side, I have a plot where the x-axis is, instead of P pre, I just wrote PA, but this is the probability of passing the preimage test. And on the y-axis, we have the probability of passing the equation test. And so we see the quantum classical threshold is also that threshold of being equal to 2 that I mentioned. So anything above this threshold up in this regime should be in the quantum proof of quantumness regime, so anything that cannot be done classically. And so we see that all of our data points here, when we ran this, were all above this threshold. So this is indeed a proof of quantumness as long as these cryptographic assumptions are not broken. And we see all of these different instances that I mentioned are just different choices of those matrices that I mentioned. And moreover, we implement this with two different types of measurements. So one is this interactive measurement and one is delayed. And what I mean by that is in the interactive version, remember that we require this like commitment, and then we need to choose whether or not to have Hadamard gates and then measure again. So this can be done experimentally via mid-circuit measurements, and that's what the interactive measurement is. Meanwhile, the delayed measurement is just considering if we just push all of those measurements to the end and just do it in a single shot all at once. And this was mainly to see how much do the mid-circuit measurements actually affect the computation. And we can see that here the interactive measurements are all lower, have lower probability of success than the interactive measurements, which gives motivation for the non-interactive version of the protocol that I'll talk about in a bit. And also on the right here is just a breakdown of all of these probabilities step by step. And so these different branches correspond to the different preimage or equation tests. And the relative performance here just means we're comparing it to, say, a classical prover that just guesses at random. Okay, and this was for the learning with errors protocol. And I'll also show, even though I didn't specifically talk about the factoring protocol, I'll show the results for it as well. And so we did fewer instances for this case, but we see that most of the data points still pass the quantum classical threshold, and there is this one outlier point here that didn't pass, and the main reason for that was because we had to do a lot of optimizations in order to, or approximations, I mean, in order to fit it into the number of qubits allowed. And so that resulted in much lower success probabilities. And similarly, we have this breaking down of each of the different probabilities, and we see that this more complex branching structure reflects this additional round of interaction that I said was necessary. And now I'll talk about the non-interactive protocol. So like I mentioned when I was talking about the results, interactivity with these mid-circuit measurements is often difficult to implement experimentally. So we saw that the delayed measurements often had a much higher success probability than the interactive versions. So then we asked the question, can we get a cryptographically secure non-interactive protocol? So in particular, we can't just do this delayed measurement of like pulling everything down to the back of the circuit and just doing a single shot measurement at the end. That technically isn't cryptographically secure. And that's why I mentioned just doing it to see, oh, can we see how this compares to the interactive measurement case? So we need a new protocol in order to do this. And the idea is to use cryptographic hash functions to replace the interaction. And this is something known as the Fiat-Shamir heuristic in cryptography. And so what we then do, what I mean by this like non-interactive protocol, is there's no longer these multiple rounds of communication. There's no like challenge and response and so on. It's really much more simple. And what happens is that the verifier first just sends over the setup and the question that they want. So essentially just combining the setup and the challenge steps into one. They send that over to the prover, and all that the prover then does is sends over their response. Okay, and this is the overall structure of the protocol, but I mentioned that we need some cryptographic hash functions. So in addition to the trapdoor call free function, we need this additional assumption. And this is called, so this is the hash function. And in this paper, we propose, instead of using some more standardized hash function like SHA-256 or something like this, which obviously wouldn't be implementable on current computers, then we propose using a heuristic instead, which is just a small random circuit, and see how this does. And in fact, it does work. And in particular, this is the quantum circuit that we use, so it's just a bunch of controlled set operations. And this is an equation form of the actual hash function. So the protocol is as follows. So again, we still have the verifier and the prover. And what happens first, the verifier, again, just generates the TCF together with their trapdoor. And all the verifier needs to do is they send over this F to the prover. And the prover sends back, this time, a pair of two outputs. And this pair is the bit string D along with Y. And they serve essentially the same same purpose as they did previously. So in particular, the check that the verifier has to perform is this. So they need to check, does D.x0 XOR x1 equal the hash function evaluated at x0 XOR the hash function evaluated at x1. So this is almost the same equation as before. Remember that the equation from before was the same thing, except we had to check if this was equal to 0 instead of this evaluation of the hash functions. And the way that you can think of this is we got rid of the preimage test completely, but we're kind of encoding it as into this hash function. So if we knew some random information, so the hash function evaluated at each of the preimages, then that's essentially the same as knowing those preimages themselves. And so that's why we can kind of get rid of the preimage test. And again, this is efficiently verifiable, just because using the trapdoor, again, we can find these x0 and x1s corresponding to the y that the prover sent over. And we can evaluate the hash function on these x0 and x1s and just check the equation. And again, the quantum strategy for this, let's talk about how a quantum computer could implement this perfectly. And once again, I have a quantum circuit here. So remember, the first register was for the inputs, and the bottom register is for the outputs of the function. And again, we just implement evaluating the TCF on a superposition over all possible inputs. And the only addition here that's different from the equation test was this evaluation of the hash function. So that's what I have as this UH. And remember that it's this small random circuit. And then we Hadamard again, just like in the normal equation test from the previous interactive protocol. And then we measure. And this is indeed a single shot measurement. We don't need any of the fancy mid-circuit measurements as from before. And when we measure the top register, we get the bit string D. And when we measure the bottom, we get the output Y. And it turns out that the Another good reason to use this protocol instead of the interactive one is because there is no longer this really complicated threshold inequality, and instead we just have the best possible classical success probability, again assuming our cryptographic assumptions are not broken, is 0.5. So we no longer have this like p pre plus 2 PEQ is less or is greater than 2, but we instead have this just 0.5. And so when we ran this on an ion-trap quantum computer, then we have the following results. So here we're just breaking up all the data points into these experimental repetitions. So it's just batches of like 2,000 shots just to see how it performed over time. And on the y-axis, we have the success probability. And notice that the bottom of this y-axis is this 0.5, so that's the classical threshold. And again, the instances are just, we only performed this version of the protocol for learning with errors. So these instances correspond to different learning with errors instances, so different choices of matrices and vectors. And again, we see that, yeah, all of these data points are significantly above this 0.5 threshold. And if we compare that to the previous case, they all have a much higher statistical significance of being above this threshold as well. And that indicates the ease that these non-interactive protocols could be a lot easier to implement and to scale up than the non-interactive version. Okay, so now I'll wrap up what I summarized what I talked about today. So cryptographic proofs of quantumness really allow for this efficient verification of quantum advantage once at scale, so the verifier can efficiently verify these results. And these are the first such demonstrations of implementing proofs of quantumness on current quantum computers. And there are many applications to this, so I'll talk about a few of those. So one that I've kind of mentioned throughout the talk is verifiable quantum advantage once you scale this up. Another that's of interest is certifiable random number generation. So this is where you have a quantum computer or a supposed quantum computer that's generating some random numbers, and you want to see, are they actually random or are they pseudo-random? And this is, again, another task for quantum advantage because classical computers can't generate any truly random numbers. And another is verification of arbitrary quantum computations. So there are a lot of protocols out there that do this. And all of these different applications use these same either interactive protocols or their non-interactive versions. And so by showing this sort of proof of principle result, then we could possibly show hope for generalizing this further. And of course, there are open questions. So one is obviously implementation at scale. How can we scale this up? And are there more efficient constructions? So recently there have been some works on short depth or low depth different protocols for similar tasks. And one open question is, both in theory and in practice, could we either implement these efficient constructions or come up with better ones? And finally, I would like to acknowledge everyone who was a part of this collaboration, so mainly us theorists at Caltech and UC Berkeley, along with Chris Monroe's experimental group at UMD and now Duke.
Thank you very much. Questions from the audience?
Thanks very much. That was a really nice talk. When you were talking about using this to verify quantum advantage at scale, so the thing about a lot of these cryptographic results, like self-testing or Mahadev protocol, they're all really scalable in terms of measurement effort and classical computation, which is great, but they kind of don't scale in terms of robustness. Right? Like by definition, a NISQ device just gets worse and worse the bigger it gets because it doesn't have error correction. And a lot of these results, it tells you if your system is good, but once it becomes somewhat less good, it just tells you it's bad and you don't get too much more information about it. So, I mean, I don't know, whatever the number of qubits is where I have quantum advantage, 10 or 50 or some, do you think, for instance, for this ion trap, if I had a big enough system that I couldn't simulate it, would it ever pass these tests? Would I ever actually be able to win the game and beat the classical threshold?
I hope that it would. Yeah, I think that I think there's more hope for the non-interactive test, just because, so actually, when we were, let me see, when we were implementing these things, because I think like some intuition that we had was essentially that the non-interactive test, or just the equation part of the test, had some kind of like noise resistance almost built into it, kind of because of learning with errors. But essentially the reason was because when we did the pre-image test, then often we would get very, very low probabilities on the pre-image test, but it was really the equation test probability that managed to like pull it up past the threshold. And so I think the reason kind of for that is probably because in the equation test, we really only need to check if a single bit is right? Because we're doing this like d dot x0, xor, x1, and that just turns out to be a bit. And we're just checking if that's 0 versus 1. And so that's a lot easier than checking if the entire preimage is right. So I guess that was kind of a long answer for your question, but I think that there is probably more hope for this because it seems to have some noise resistance built in.
Thank you. That was very interesting. Thanks.
I think we have time for another question.
Thanks for the talk. I have a small question about the like hash function unit arrays you put on the circuit, but you put behind it like your functional circuit. But I'm curious if you change your like hash function unit arrays, would these results like the different results, or you change like the position of your hash function unit arrays to other place? For example, before like your unit arrays like circuit, would this have a difference of your results? I'm just out of curious.
Yeah, as long as so this was just a hash function that we happened to choose for this, but the gates were actually randomly sampled. And essentially, as long as this circuit is like random enough, then it will be able to function. It will be able to be a proper hash function, and the result will go through.
And then would this matters if you put your hash function in other positions, like in the circuit, for example, before your unit arrays function unit array? Or
Yeah, you mean like how it has to be here?
yeah, it hasn't been here, but what if you put it in front of UF? Like
Yeah, I guess like cryptographically, it only really makes sense for it to be in that position.
okay.
Yeah, just like based on how the protocol is arranged.
Okay, thank you. Yeah.
I just want to return briefly to the previous question, actually. So maybe another way to ask what's on my mind about scaling is there a path that you might see in which the classical probability decreases as the problem gets larger?
I'm not sure, actually. Yeah, that's a good question. I don't think so. Yeah, these thresholds are like the ones that are known. Yeah, I don't know if there's one where like the classical threshold would decrease, but the quantum threshold would be still like perfect. I do know of protocols where like I think the classical threshold might be lower, but the quantum one is also not perfect.
All right. Let's thank Laura again.